We will be discussing graph of a relation. Now, first let us see what is a graph. If we have a pair of sets G V E, where V E are two sets, we call it a directed graph, or in short a digraph, if this set E is a subset of V cross V. The elements of V are called vertices and the elements of E are called edges. An edge x y is said to be from x to y and is represented in a diagram with an arrow with a tail at x and of course, the head at y. Now, let us look at examples of such graphs. So, first we will be writing the vertices as points on a plane. So, let us say I draw a point, call it A, another point let us say I write B, another point I write C, and let us say D is another point. Now, we can in fact draw any directed edges from any vertex to another. So, starting from A, let us suppose we write A B. So, it is a directed line from A to B. This is what we will call a directed edge. And this is exactly what we will denote by the ordered pair A B. Now, let us draw one more A C, and we can also write an edge from C to A, then possibly B to D and C to D to C, and also C to D and B to C. So, what we have done here is that we have drawn some arbitrary directed edges from the vertices. We can write them as ordered pairs, as the first one as I have already written A to B, and then A to C, then let us see nothing more on A, then we go to B, then we have an edge from B to C, then we have an edge from B to D, B D, then from C we can go to A and also to D, and finally, we have an edge from D to C. Now, the set of vertices is A, B, C and D, and the set of edges is A B, A C, B C, B D, C A, then C D and D C. We combine these two sets to write the directed graph, which is V E. What we note here is that this is naturally a relation, because let us recall, suppose we have the set V, which is as we see A, B, C, D, and suppose we talk about relations on A, relations on V. So, a relation on V is nothing but a subset of V cross V, and the set E is exactly a subset of V cross V. Therefore, it is a relation on V. Thus, a directed graph gives me a relation on the set of vertices. On the other hand, it is quite natural that if I have a relation, then I can take the set on which the relation is defined, and then take that relation itself will give me the set of edges of the directed graph. So, with respect to a relation, we always get a directed graph. Now, here there is something we have to note, that sometimes instead of a relation on a set A, we would like to look at a more general situation where we are talking about relations from A to B, and that also does not make any make much difference over here, because what we can do is the set of vertices can be chosen to be the union of the two sets A and B. That is, suppose I have a relation from A to B, I may choose the set of vertices to be union of A and B, and then I can consider R not as a subset of A cross B, but a subset of A union B cross A union B, and it is not difficult to see that a subset of A cross B can be embedded in a subset of A union B cross A union B, and thus from there we can get the digraph corresponding to the graph to the relation from A to B. Now, let us try to build graphs of some relations. Now, let us take one graph let us take one relation on set of people. Let us call that relation is parent of. Suppose we denote a set of people by A, B, C, D, E, F and up to K, and the relation R is parent of relation, and suppose we have a listing like this. So, we have R, which is subset of ordered pairs like A, E, A, F and so on up to I k. Here A, E means A is parent of E, A, F means A is parent of F, B, E means B is parent of E, B, F means B is parent of F and so on. Now, we would like to draw a graph of this relation. First, we write the set A B set S. Now, see, this is A, the vertex A and the vertex B, and then the vertex C and the vertex D. And now, let us write the listing over here. Here we see that R is equal to A E AF, BE, BF, CG, CH, then we have DG, DH, FI, FJ, GI, GJ, JK and IK. So, let us look at these two ordered pairs. So, AE and AF are in the relation. That means that we draw two more vertices, name them as E and F and join A to E. That means A is a parent of E, and then join A to F, which means that A is a parent of F. Then we see that we have BE and BF, therefore, we join B and D, draw a line over here, B and F, draw a line and an arrow. So, this means that B is a parent of F and B is a parent of E. Now, we come to the next two pairs, this is CG and CH, and after that we have DG and DH. So, we write G over here and H over here. So, we join CG and CH, which means that C is a parent of G and C is a parent of H, and then we join DG and DH, and that exhausts the relations up to this. Now, then next we have Fi and Fj and Gi and Gj. So, we draw I over here Fi and we draw a point j over here, we have Fj, then we join Gi and Gj, and lastly we have Jk and Ik. So, we draw another vertex over here which is k and join I to k, this is Ik and this is Jk. Thus, we have a graph corresponding to the relation is parent of, and where the listing of the people is given in the set S. Now, let us look at another example. Here we are asked to draw the digraph of the relation divides defined by A divides B if and only if there exists a positive integer C such that A into C is equal to B, and the set of integers on which this relation is defined is 1, 2, 3, 4, 5, 6, 7, 8. So, that is positive integers from 1 to 8. Now, this divides is a usual division on the set of integers. So, first thing that we have to do in order to solve a problem like this is to write all the ordered pairs corresponding to this relation. So, we shall do that shortly. Now, let us consider the set, let us call it for the time being S. This is 1, 2, 3, 4, 5, 6, 7 and 8, and we write the relation in this way: A divides B if and only if A divides B. We are denoting the relation by a vertical line. Now, let us start to list all the ordered pairs corresponding to this relation. So, we have got R. Now, let us start with 1. 1 divides all the integers in the set S. So, 1 comma 2, 1 comma 3, 1 comma 4, then 1 comma 5, 1 comma 6, 1 comma 7 and lastly 1 comma 8. Then if we start with 2, we have 2 does not divide 1, but 2 divides 4, it does not divide 3 either, 2 does not divide 5, but 2 divides 6. So, we have got 2 4 and 2 6, 2 does not divide 7, but 2 divides 8. So, we have got 2 8. So, we finish up with 2, then we start with 3. So, 3 divides 6 and nothing else, then we come to 4 divides 8 and 5 does not divide any other number in S, 6 does not divide any other number in S, neither does 7 or does 8. So, we have the complete listing over here. Now, we have to be bit careful about drawing the graph, because it may become very messy if we are casual about putting the vertices. So, first let us observe 1 is related to many elements and no element is related to 1. Therefore, what we do is that we draw first the point 1 over here at the very bottom and write 1, and then we see that all the other elements 2, 3, 4, 5, 6, 7 and 8 are related to 1. So, first we write 2 like this, 2 and draw an arrow. Then we try to see from here whether 2 is related to something else. Yes, here 2 is related to 4. So, we write 4 over here and join by an arrow. So, 1 to 2, 2 to 4, and then 6 is also there and 8 is also there, but here we see that 4 is also related to 8. So, what we do is that we draw a point, the point 8 over here, join from 4 to 8 and also join 2 to 8. So, we have completed 1 going to 2, 2 going to 4, 4 going to 8 and 2 going to 8. And now, we start off with 3 and 6. See, 3 is related to 6 and 2 is also related to 6. So, we have to keep space for that. So, we may like to draw 3 over here, all right, and possibly it will be a good idea to draw 6 over here and join 2 to 6 and 3 to 6. At the same time, I have to join 1 to 6 because that is also there, and we must remember to join 1 and 8 because it is also in the relation. Therefore, see, we have done 1 3, then 2 6, then 3 6, then 1 6, and we have also taken care of 1 8. So, we have not taken care of 1 4, but we shall take care of that shortly. This is 1 4, and after that we are left with 1 5 and 1 7, that we can do by drawing 2 other points 5 and 7 and joining 1 to 5 and 1 to 7. This is the graph corresponding to the relation A divides B on the set 1 2 3 4 5 6 7 8. Now, let us look at more examples on graphs of relations, namely this. Now, our set is 0 1 2, the 3 element set 0 1 2, and a digraph we have to, a relation is defined on it, which is the subset of relation, not on the set 0 1 2, but on the set of all non-empty subsets of 0 1 2. So, our problem is to draw the digraph of the relation subset of or equal to on the non-empty subsets of the set 0 1 2. Let us try to do that now. Here, let us write the set 0 1 2. The first step over here is to list all the non-empty subsets of 0 1 2. If we call this set S, then the set of all non-empty subsets will be P S minus the set containing phi, the empty set. Now, let us start listing. First, we will write the all the singleton subsets, then we will write the subsets of size 2 or subsets of cardinality 2, 0 1 0 2 and 1 2, and finally, we write the subset 0 1 2. Now, let us write the elements which are contained in the relation subset equal. We are denoting the relation by the symbol. This is after all a subset of the power set minus the set containing phi. So, it is equal to ordered pairs. Let us see, let us start with the element set 0. This element is a subset of 0 1, then 0 2 and 0 1 2. So, therefore, in the ordered pairs we will have 0 1 comma 0 set 0 comma set 0 1, then we will have set 0 comma set 0 2, then we will have set 0 comma set 0 1 2. Next, we will start with the singleton 1, and then the singleton 1 is a subset of again 0 1. Next, we consider the singleton 1, it is a subset of 1 2. Then we consider the singleton 1 again, and of course, this is a subset of 0 1 2. All right. Then we have got singleton 2. 2 is a subset of 0 2, then 2 is a subset of 1 2, right, and then 2 is a subset of 0 1 2. Finally, we start taking the we have exhausted by starting with the singleton sets, and then we take sets containing 2 elements. So, we have now 0 1, and we see that 0 1 is contained in 0 1 2. So, the pair 0 1 0 1, so the pair 0 1 0 1 2 will appear over here, and then we will have 0 2 that is contained in 0 1 2, and finally, we have 1 2 which is contained in 0 1 2, and we close the bracket. So, these are the relation these are the elements of the relation subset equal on the set containing all the non-empty subsets of the set 0 1 2. And now, we would like to draw the digraph corresponding to this relation. Here again in practice, we start from an element which is related to all the elements, but no other element is related to itself, and that element in fact there is no single element like that over here. There are 3 elements like that which are essentially the. So, see, we have written 0 over here, all right, and 1 over here and 2 over here. Then we have written 0 1 over here, and we have joined these lines. Okay. the 0 2 we will write over here. We will join 0 to 0 2 and here 2 to 0 2, and then we will write 1 2 over here, this is the point, and join 1 to 1 2 and 2 to 1 2. Thus, we have a nice shape. In fact, when we are drawing a digraph of a relation, we have to take this into mind as well, that we have to keep in mind that whatever diagram we are drawing, it should look nice. And now we have only one element left, that is again let me remove this. We have got only one element left, that is 0 that is 0 1 2, and then we see that 0 1 is a subset of 0 1 2, 0 2 is a subset of 0 1 2, and 0 1 2 is also a subset of 0 1 2. Thus, we get the digraph corresponding to the relation wait a moment, it is not complete yet, there are some more things that we have to do. We have missed out few things. For example, we have missed out this one. So, we have to connect 0 to 0 1 2 because they are related. Yes, we have to connect 1 to 0 1 2 and we have to connect 2 to 0 1 2. Now, we have got all. We can check that because we have got starting from 0 to 0 1 we have done this, 0 to 0 2 we have done this, then 0 to 0 1 2 we have done this, then 1 to 0 1 we have done this, 1 to 1 2 we have done this, and 1 to 0 1 2 we have done this also. Then 2 to 0 2 we have done this, 2 to 1 2 we have done this, and then 2 to 0 1 2 we have also done this. Now, 0 1 is related to 0 1 2, 0 2 is related to 0 1 2, and 1 2 is related to 0 1 2. Thus, we have completed completed the scanning the whole list and drawing the corresponding directed edges. Now, let us look at another example. We are asked to draw the digraph corresponding to the relation not equal to on the set 0 1 2. How will we do that? Here we are starting from the set, let us call it S, which is 0 1 2, and our relation is not equal to. So, if we try to write the set corresponding to the relation, let us write like this. So, 0 is related to 1 and 1 is related to 0. Then we have 0 is related to 2 and 2 is related to 0. Then 1 is related to 2 and 2 is related to 1. Then we have got 3 points on the set. So, we write the 3 points, suppose like this is 0, this is 1, this is 2. So, here we see that 0 is related to 1. So, we have to write an edge like this 0 to 1. I also write an edge like this 1 to 0, then 0 is related to 2 and 2 is related to 0. So, I write 2 more edges, and then we see that 1 is related to 2 because 1 is not equal to 2 and 2 is related to 1 since 2 is not equal to 1. Thus, we have got a nice shape over here of the digraph. Now, we look at some examples of digraphs. Now we will check some definitions related to digraphs. An edge from a vertex to itself is called a loop. So, we will see examples of loops. A digraph with no loops is called a loop free digraph or a simple digraph. Next we will try to write down some relations from a graph, but let us check now. We have already seen this digraph what is happening. So, in the last example we have already seen this digraph 0 1 2 like this. Now, this is loop free because there is no edge which starts from a vertex to another vertex, but if we have an edge like this, for example, in this way, so then it is a digraph with a loop. This is a loop. Similarly, we have a loop like this. Here we have to we observe that suppose we have a relation which is reflexive, then each of the vertices of that relation will have a loop around it. For example, if we make another loop over here, then the corresponding relation will become reflexive, because that will mean that each element is related to itself. Now, we may also have some problems where we are given a digraph on a set of vertices and asked to write down the corresponding relation. For example, here we are starting with the set of vertices A, B, C, D, E, and then we are given a digraph. Now, it is quite straightforward problem, because we see that we can start with A, and of course, A B, the pair A B is in the relation and no other pair starting from A. So, we write A B over here, then we start from B, there is no edge coming out from B, therefore, we do not list anything. Then we come to C, we see that there are 4 edges coming out of C. So, C A, C B, C E and C D. So, we write over here, and then we have got D A, and then EB and ED. So, we have the relation corresponding to this digraph. There are some more definitions related to digraph, that is in degree and out degree. Suppose we have a vertex x, in a digraph the number of edges coming out of x is called its out degree, and number of edges incident on x is called its in degree. So, if we look at a graph that we have already studied, let us say this one. All right. So, we have a graph. Now, let us consider the vertex A. So, number of edges emanating from A is 1. So, out degree of A is 1 and in degree is the number of edges incident on A. Here we see that this is 1, 2. So, this is 2. Similarly, we can make a list of in degrees and out degrees. In degree, out degree, and vertices A, B, C, D and E. We have seen that for A it is 2 and 1. For B, let us consider B. B there is only in degree, so that it is 3 and out degree is 0. Then in C all are out degrees. So, we have got 4 and no in degree. D in degree is 2, out degree is 1, and E in degree is 1 and out degree is 2. Finally, we come to the idea of isomorphism of digraphs. Suppose we have two digraphs G1 given by the pair V1 E1 and G2 given by the pair V2 E2. Now, we will call the two graphs isomorphic if there exists a one to one function f from the set of vertices of G1, namely V1, to V2, the set of vertices of G2, such that the ordered pair VW belongs to E1 if and only if the ordered pair FV and FW belongs to E2, and this function f is said to be a graph isomorphism. In general, it is a difficult problem to decide whether two graphs are isomorphic or not, but there are some properties of graphs which are called invariants, through which we can take decisions at least towards one direction. So, here we introduce an idea of invariance. An invariant of a graph is a function g on digraphs such that G1 equal to G2 whenever G1 and G2 are isomorphic. Now, the invariants can be number of vertices, the number of edges, or the degree spectrum, which is the collection of all in degree out degree pairs of all the vertices. So, this means that given a graph, I can always compute these things. For example, I can always compute the number of vertices or number of edges or the degree spectrum. Suppose there are two graphs for which these numbers do not match, then we are sure that these graphs are not isomorphic, but if they match, we cannot be sure, we cannot take any decision. However, it is known that if two graphs are isomorphic, then all the numbers will match. Therefore, if the numbers do not match, we can say they are not isomorphic, but if the numbers match, we cannot say anything, because there are examples of non isomorphic graphs for which all these numbers match. So, in this area, it is an important problem to find out different invariants, so that we have got good resolution among the set of graphs. I will stop the lecture now. We have studied how to build digraphs from relations, and we have also seen, given a relation, we have also seen given a graph how to convert that to a relation. We have also seen some examples of graphs of relations and relations from digraphs, and finally, we have discussed certain properties of these digraphs. This is all for today. Thank you.